We would like to talk about the single phase transformer. Um, yeah. So the working principle in this subject, in this chapter, we'll talk about the working principle of, sorry, let me find my laser pointer. Okay, we'll talk about the working principle of a transformer, types and construction of transformer. There are core types transformer, shell type, types of transformer, and then we'll cover the magnetic core of a transformer, primary, secondary windings, ideal transformer, power in the ideal transformer, impedance transformation. And then we also talk about the theory of operation of the real single-phase transformer. It includes the voltage ratio across the transformer, magnetization current in the real transformer, the current ratio on the transformer, and the dot convention. Then we'll go to the practical transformer. We have hysteresis and eddy current losses. We have a reduced hysteresis losses. We have a reduced eddy current loss, reduced copper loss. And then next we'll talk about the equivalent circuit of a transformer, the exact equivalent circuit of a real transformer, and the approximate equivalent circuit of a real transformer. We also cover the open and the short circuit tests. Open circuit test is a no load test. Short circuit test is a impedance test. And then we have a per unit system of measurements. We also cover the transformer voltage regulation and efficiency. Transformer voltage regulation, phasor diagram, and efficiency. And then the last part will be the auto transformer, voltage current relationship in an auto transformer, and apparent power rating advantage of an auto transformer. So the working principle of a transformer. An electromagnetic device. It is an electromagnetic device. Play about the electric convert to magnetic, or magnetic convert back to the electric, and then works on Faraday's law of electromagnetic induction. And it is a transformer is an AC static machine that functions to transfer electrical energy from one electrical circuit, we call primary, to another one, secondary, through magnetic domain without changing the frequency. So this is the transformer winding. We have a primary winding, secondary winding. So the primary winding will connect it to the AC voltage source. The coil at the source is called primary winding. The coil at the load is called secondary winding. So the primary winding will connect to an AC voltage. Then we have a BP, we call it as primary voltage. We have a IP, primary current. We have the NP turns, primary winding. Then we have a secondary voltage, VS. We have a secondary current, IS. Then we have a secondary windings, NS. Then when we inject connected to the source, a current flowing through the coil by using the Fleming right-hand rules, it will create a flux. Then the flux will transfer from one point in the core, then come to a secondary side, and then go back to the core, the primary winding there. And then this is how they transfer the energy. They convert all the electrical energy into magnetic, and then flowing through a core, then from magnetic to become electric. So that's why we call electromagnetic devices. So it consists of two inductive coils which are electrically separated but magnetically linked. The two coils possess high mutual inductance. The first coil, in which electrical energy is fed from the AC supply, is called primary winding. The other winding, where energy is drawn, is called the secondary winding. The rate of change of flux results in an induced voltage in the secondary winding. If the secondary winding is connected to a load, the induced voltage will drive a secondary winding. Well, the secondary current and the voltage may or may not be the same as the primary depending on their types, but the power is the same if the transformer is lossless. The flux in the core will always be constant in no load and loaded conditions. The transformer are bidirectional devices. Both windings can be used as primary when connected to an AC source. Transformers are also used for a variety of other purposes. For example, voltage sampling, current sampling, and impedance transformation. But this chapter is primarily devoted to the power transformer. So types and construction of transformer, we have a core type transformer, we have a shell type, we also have a, we talk about types of transformer as well. So from here, we have a core type, we also have a shell type. When we put in when we cut the cross-sectional we have a core type construction, we have a shell type construction. Let's have a look on the core type construction. So we have a high voltage winding, we have a low voltage winding. This is low voltage, high voltage, high voltage, low voltage, low voltage, high voltage. And then the flux created will flow into the core. That's why we call a core type transformer. Then another one is a shell type. We have a high voltage, we have a low voltage, or low voltage or high voltage. Then the flux will flow through from center to the left side and right side, where the flux has been divided into two. So this is, for example, this is flux. This will be flux divided by 2. Flux divided by 2. While on the core type construction, the flux flowing through in the core, are the same. Okay. So for the core type transformer, it can be illustrated as like this. Core type transformer. Half of the primary winding and half of the secondary winding are placed one over the other, concentrically on each leg. Concentrically means it covers one leg, like this, or it covers like this, concentrically. And then to increase the magnetic coupling, allowing practically all the magnetic lines of the force go through both the primary and secondary winding at the same time, which means this core type can increase the magnetic coupling. What do you mean by magnetic coupling? Coupling means connected, connected. Which means, for example, the flux I generated here, it will flow through here and then converted to electrical energy here, and then also will flow back here, So this is how they call magnetic coupling. There's no direct connection for the magnetic to here, from here to here, but the energy can be transferred from primary to winding. That's what primary to secondary. This is called magnetic coupling. We connect the primary magnetic flux and also the secondary magnetic flux. And then, this core type, it will increase the magnetic coupling. With this type of transformer construction, a small percentage of the magnetic line of the force flow outside of the core we call as a flux leakage. So in a transformer, we would like to make sure, if there's a good transformer, the flux that generated in the core should go to transfer from one side, primary side, to the secondary side, all. For example, here we have a 1000 line of a magnetic flux. We hope that the other end can receive 1000 line as well. This is called a very good perfect magnetic coupling. But in fact, it is not. There's a losses. We call it is due to the leakage of the flux, where some of the flux it cannot flow through from this primary side to secondary side as 100%. For example, 2%. 2% of the flux will flow outside from the core through the air and then going back. So we can see that the primary flux, that leakage, it will go to outside and then coming back to the primary. For this side, it is not connected to the secondary. So energy will be lost. Okay? That's why this is called leakage flux. This is also called leakage flux. We have a primary leakage flux like this. We also have a secondary leakage flux like this, where we call it will make losses. Next, the shell type. Okay, this type overcomes leakage flux as both the primary and secondary windings are wound on the same center leg or limb. It wound together at here. So no matter the flux flowing through where, it will just go to left side or right side. That's why the leakage is less. And then, but it has twice the cross-sectional area of the two outer limbs, which means if let's say the length here is 10 cm, here will be 5 cm. Because I just need to have half of the flux flowing through outside of this one. However, I need 2 times of the flux flowing inside in here. So if let's say I have a 2 cm length here, here I must have, center one I must have at least 4 cm. So the advantage is the magnetic flux has two closed magnetic paths to flow around the external to the coil on both left and right hand side before returning back to the center coil. This is the advantage, flowing through the left hand side or flowing through the right hand side and then go back to here. This means that the magnetic flux circulating around the outer limbs of this type of the transformer construction is equal to flux divided by 2. If let's say I have a 10 Weber here, it will divide by 2. It becomes 5 Weber here and another 5 Weber here. As compared to the previous one, if I have a 10 Weber here, we hope that we can receive another 10 Weber on secondary side. Okay? So, and then as the magnetic flux has a closed path around the coil, this has the advantage of decreasing core losses and increasing overall efficiency. So as a comparison between the core type and the shell type, this one is core type. The magnetic coupling is low. Coupling, connecting, which means how good we transfer the primary magnetic field to the other side, to the secondary side. Low means the connectivity is very low. For example, I have a 10 Weber here. When transferred to here, it might be 8. If compared to the shell type, it has a high magnetic coupling, a decreased flux leakage, low flux leakage, which means if let's say I have a 10 Weber here, I might have a 5 Weber here, 5 Weber here. There's no losses or less losses. And then for the core type, it's a high core loss. For the shell type, it's a decreased low core losses. And then for the core type, we have a high low efficiency. For the shell type, we have a high efficiency. Yeah, just a general overview of the types of transformer. From the power generation, the voltage generated from the power station A connected to the transmission. Before that, it has a power transformer we call unit transformer. We used to step up the transformer to 11 plus kilovolt, and then after that we'll go to the transmission substation. We have a substation transformer which used to step down the transformer from step down the voltage from 11 kilovolt to 2.3 kilovolt range, 34.5 kilovolt, and then transmitting to distribution substation. At the distribution substation, we have a distribution transformer also stepping down, either deliver to the commercial or industrial business consumer, or deliver to the distribution automation devices with maybe 1110 volt, 208 volt, 220 volt, stepping down from 2.3 kilovolt range of 34.5 kilovolt to 110 volt, 208, 220. And then we also have a potential transformer and current transformer. These two transformers are used to measure measuring the voltage or current. We call it as a instruments transformer. So as an overview, we have a unit transformer, we have a substation transformer, step down transformer, we have a distribution transformer, maybe step down transformer, only unit transformer is stepping up, and then we have a potential transformer and current transformer as an instruments transformer. Next, we'll talk about magnetic core of the transformer. So three main types of steel core. We have a solid iron or steel, we have a laminated silicon alloy, silicon steel, we have amorphous steel. For solid iron or steel, it is a strong magnetic field but produces large eddy currents and heat. So this is not very good. Then for the laminated silicon alloy or silicon steel, it allows efficient magnetic propagation, reduce eddy currents and heat dissipation. And another one is amorphous steel, extremely thin strips, and the eddy current greatly reduced at a mild to high frequency. The best one is amorphous steel, but it's not. It's very expensive and it's not what we call. It is fragile. It's very easily to be broken. Broken. So usually we use a laminated silicon alloy or silicon steel to do it instead of using the solid iron. Then, okay, laminated magnetic core. Circulating currents we call as an eddy current. This one is called circulating current with a laminated low eddy current. For example, this core, if I cut here, then I will see this one. So we have a many laminated core. This is one steel sheet, one steel sheet, one steel, one steel, one steel. And then when there's a AC coil here, it will generate the fluxes flowing through inside the core. It will generate the eddy current. That's why we call eddy current. It will cause heating and energy losses within the core, decreasing the transformer efficiency. So it will heat up this core. One way to reduce these unwanted power losses is to construct the transformer core from thin steel lamination. If it is a round core, then the current will flow through like this. Then the losses will be higher. If compared, then if I having the same area, I cut into pieces, then the current flowing through inside this small area. When the current flowing through small area, the losses will be lower as compared with if the current flowing through in a bigger area. So this is one way to reduce unwanted power losses. In all type of transformer construction, the central iron core is constructed from a highly permeable material made from thin silicon steel lamination, assembled together to provide the required magnetic path with a minimum of losses. The high resistivity of the steel sheet means kepingan steel itself, kepingan steel besi itself reduces the eddy current losses by making the lamination very thin. For example, if let's say I'm not happy with 5 laminated steel, I can make it become 10, double up, or 8. The higher the laminated steel per same area, then the lower the power loss. Primary and secondary winding. A varying current in the transformer primary winding create a varying magnetic flux in the transformer core and a varying magnetic field impinging on the secondary windings. This varying magnetic field at the secondary winding induces a varying EMF on the voltage in the secondary winding due to the electromagnetic induction. Okay, which means if I inject the voltage AC mode, DC, that means the current just flowing through one direction. If let's say go inside like this, okay, using Fleming right hand rules, the flux will go top, then the flux will flow to the top, then go to the secondary side and then come back. Okay, this is DC. So there's a one way. If it is AC, means now it go into this direction. So the flux will go to this direction. And then after that I change to this direction. Then the flux will reverse direction. Right? So yeah, if I keep changing one direction, it will flow like this. Then another direction, it will flow like this. So which means if I vary the current in a winding, the fluxes also will vary. Either if it is AC, then the fluxes will go back in clockwise or counterclockwise. Okay. This is what they call a varying current in the transformer primary windings create a varying magnetic flux. And then when there's a varying, means the flux will go here from the top to the bottom, and then from the bottom to the top for many times. The flux will cut the secondary winding. When there's a cutting on the secondary winding, it will induce voltage. This is why they call the varying magnetic field at the secondary winding induces a varying EMF. So the EMF generated here will be an AC as well, because it is varying. AC current inject in the primary winding, it will create AC clockwise and counterclockwise magnetic flux. And then the clockwise and counterclockwise magnetic flux cutting the secondary windings, it will generate a varying EMF. We call it as a AC EMF. So for example, now I have 100 volt VRMS, 10 ampere ARMS, and this is a 1000 watt. We assume that it is a lossless transformer. So 1000 watt transfer to secondary will be 1000 watt. And if I need the rated voltage at the secondary side is a 400 watt, the ampere that I will get is a 2.5 ampere. So we can see that this is a step up transformer from 100 volt to 400 volt. And then this is a step up transformer where the number of the primary winding will be less than number of the secondary winding. So primary winding will be less than the secondary winding. At the same time, voltage for the primary side will be less than the secondary side. This is called step up. In contrast, if stepping down means if let's say I have 1000 volt, I want to have a 200 volt, same wattage, 200 watt, 2000 watt to 2000 watt, no losses. Okay, the primary winding I need must be much more than the secondary winding. For example, this is 50 turns, this is 10 turns. So that my VP will be bigger than VS. This is a step down transformer. So can the transformer has the same number of winding at the primary and secondary, which means that the VS and VP are the same? Answer is a yes. It is called the isolation transformer. Isolation transformer isolate it, which means if let's say this is short circuit, the short circuit current will not flowing into the primary side. Or if let's say the primary side short circuit, the secondary side will not short circuit. Okay, that's why we isolate, and then we prevent damage. So for example, here I have a primary side, 20 turns, 40 volt, 2.5 amp with a 1000 watt. Secondary side will be the same, 20 turns, 400 volt, 2.5 amp, 1000 watt. And then for isolation transformer, the number NP will be equals to NS, VP equals to VS. So what is isolation transformer? An isolation transformer is a transformer used to transfer electrical power from a source of alternating current power to some equipment or device, while isolating the power device from the power source, usually for safety reason. Isolate, we don't want them to have any electrical touching. The electrical side is not connected to, from the secondary is not connected to the primary side, or in the other way around. That's why we isolate together. So we talk about the ideal transformer, and then power in the ideal transformer, impedance transformation. Okay. Oh, this is quite something. Okay, for the ideal transformer, we need to convert them what we so call the hardware into electrical side. So from here we have a primary winding, then we have a secondary winding, we have VP as a primary voltage, IP as a primary current, VS is a secondary voltage, IS is a secondary current. The problem is we need to know how we want to design which is a positive side, which is a negative side, and then it comes into a dot convention. So when we transfer into the symbol, we have a primary winding here, we have a secondary winding here, and then this is the core. And do remember that we have a dot here, dot with the primary winding, dot with the secondary winding. Okay, the dotted voltage, the primary and secondary voltage are positive at the dotted end. This is how the rules used to determine how we want to make the transformer symbol, or how we want to define a transformer. So the dot here will be positive for the primary side. The dot here will be positive for negative as a positive voltage. And then also the dot indicates the IP is flow into the dot. Primary current is flow into the dot, while secondary current is flow out from the dot. See, one is a go inside, one is a go inside, one is a go outside. And then we can see that this is with the iron core. This is without iron core, which means it's with air. It's nothing. Okay, but most important, we must have a dot. Okay, dot means that if let's say I have a dot here, the positive will be here. If I have a dot here, the positive will be here. And then VP here, VS here, and then the current will flow into the primary, the secondary current will flow out from the dot. And then when we put into the ratio, VP divided by VS, VP divided by VS, VP divided by VS is actually the number of turns divided by the number of S. We call as a transformer ratio A. Then if I times, because I assume that the ideal transformer is a lossless, means the power in will be same the power out. So NPIP. For this one, NPIP, number of turns times IP will equals the number of secondary turns winding times IS. This is another equation. This is a basic equation we need to know lah. Then IP divided by IS, it becomes 1 over A. 1 over A, and then yeah. At the same time, VP divided by VS will become A. Actually, it's come from here. VP divided by VS, it is A. The difference here is this is an instantaneous value. If you still remember that the current that inject into this coil is a varying, which means it is a waveform, XY waveform. At time 1, it might be 10 volt. At time 2, it must be 20 volt. At time 3, it must be 10 volt back. At time 4, it must be 0. It might be 0. Then at time 5, it might be negative 10. So this is instantaneous. And then we can put it as a vector. So both is a vector. VP divided by VS vector is actually equals to a transformer ratio A. Or IP divided by IS is actually equals to 1 over A. Both will be ratio. So P out is a VS times IS cos theta. As you know that one is a conventional equation. I use a primary voltage times I use a secondary voltage times a secondary current times a power factor. This is my P out of active power. Plus with just now the equation that we have, we can put like this. For example, I change the VS here become AVP, right? VS. I change the VS here become VP divided by A. I change my IS become AIP by this equation. Then I put here, I can get into cross VP times IP, VP times IP cos theta. So we can say that P input equals to VP times IP cos theta. P, whereby P out equals to V. We also can say that P out equals to VP times IP times cos theta equals to P in. P out equals to P in, which means P out will be equals to P in. And then similarly, for the this is active power. For the reactive power, Q in it will become VP IP sin theta, which is equals to VS IS sin theta, which is Q out. Or apparent power, S in equals to VP times IP equals to VS times IS equals to S out. So similar derivation for these two. And then we can change the transformation through transformer. We call impedance transformation. We want to convert the impedance through the transformer. Why we need to do that? We will I will let you know after that. So definition of the impedance is actually if I have a voltage, I have a current, then I have my impedance where my ZL equals to VL divided by IL. Then now if let's say I cut here, I want to convert everything to here, or I want to convert everything to this side. Then this is another challenge. So first of all, ZL is equals to VL divided by IL. VL means low voltage. IL means low voltage side low side voltage, low side current. VL is a low side voltage. IL is a low side current. So this maybe here lah. So my ZL equals to VL divided by IL. This Z equals to VI lah. Then my ZL will be VS divided by IS. This is my low voltage side. ZS divided by IS. Apparent impedance of primary circuit. This is my primary circuit. So if I chop here, Z will be V divided by I, Vp divided by Ip. Then I put it as a prime. So if I plus together this one and this one, it become, if I plus this one with these two. Previously we know that Vp equals to AVS, this one. Ip equals Is divided by A, Ip. So I substitute Ip here, I substitute Vp here, then I have ZL prime equals to Vp divided by Ip, which is like this. Then I found this one. Then Vs divided by Is is actually ZL. Okay, so I substitute ZL, put it here, then I find ZL prime equals to A squared ZL. This is called impedance transformation through transformer. I transfer either from this impedance to primary side, or I transfer from the primary side to secondary side. That's why we call impedance transformation with a factor of A squared. Okay, we will use it after that, not now. So the theory of operation of a real single-phase transformer, the voltage ratio across the transformer, the magnetizing current in a real transformer, the current ratio on a transformer, and the dot convention. Yeah. So just a simple sketch of a real transformer with a no load attached to is a secondary. No load means open loaded. There's no load, no resistor, no inductor, no motor connected in this side, but we inject the AC current in the primary side. So the basic of a transformer operation can be derived from Faraday's law. What Faraday is saying that if there's a change of the flux linkage in the coil, then there's an induced voltage, which means lambda is the flux linkage in the coil, which means the flux inside the core, if it is changing over time, for example, at time as t0, the lambda is 10 Weber. Time as t1, lambda may be 20. So we use 20 minus 10 divided by 1 minus 0. This is the induced EMF. So, but the flux linkage in the transformer is described as what we call this waveform. When we have a magnetomotive force, we have a flux generated, and then the flux generated across all the number of turns, it will give us a flux linkage. So since it is actually not a very constant waveform, since the flux is not constant, it is much simpler to describe the operation by assuming average flux per turn. So we take an average value, or an average is a lambda divided by n, whereby, for example, this is np, so lambda divided by np. Then the Faraday's law can be written as this. So I substitute this lambda inside this one. Then I have n, so I copy n, d phi divided by dt, which is my induced EMF. So the voltage, let's talk about the voltage ratio across the transformer. Okay, we have a mutual and leakage flux in the transformer core. For example, this is transformer. Okay, this is a transformer. The core, and then the primary winding, secondary winding. When the current injected in the coil, AC current, so the flux will flow through in the core. At the same time, there's a flux flow through outside the core. We call it as a leakage, and then we put in mathematics notation. So we have a flux M, we call a mutual flux. We have a leakage flux, phi LP, leakage flux of the primary side, leakage flux of the secondary side, phi LS. So the mutual flux is remain in the core and links both winding together. This is called mutual flux. That's why we call magnetic coupling mutual. And then primary leakage flux is the phi LP. Passes through the primary windings but returns through the air. Passes through the primary winding here and then return through the air. This is a leakage. Bypassing the secondary winding. Bypassing means go outside. Same concept goes to the leakage of the leakage flux due to the secondary winding. So from the Faraday's law, explain what will happen. At the total average primary flux, the average flux for primary is actually constitute, which is made of flux, mutual flux, and the leakage flux of the primary side, which means all the electrical side converted into flux here, it has a mutual flux, it has a leakage flux. So I plus up together. Same as well, secondary winding, all the mutual flux come here or created by this winding. We have a mutual flux, this one, and also the flux we call as a leakage flux on the secondary winding side. So we add up together. Then Faraday's law saying that induced EMF is N d phi dt. So I substitute the phi p, this equation, into here. It becomes Np d phi m dt plus Np d phi Lp divided dt. Same as well this here. Then I put another name, call it as an EPT, or instantaneous primary induced EMF. Induced EMF due to the mutual flux at the primary side, or we call induced EMF due to the leakage of the primary winding instantaneously, or with the T is instantaneous. So I also can name as a EST and ELST. Then let's focus on this side. So if let's say I want to get EPT divided by NP, I can equate as a d phi m dt like this, right? Same as well, I found that this one also d phi m dt, whereby this one I equate d phi m dt, which is EST divided by NS. So I can put in one equation like this. Then I take out these two. So EPT, EST, I use this one, put here. I use this one, put here. It becomes NT divided by NS, which is equal to our transformer turn ratio. So the ratio of the primary voltage caused by the mutual flux to the secondary voltage caused by the mutual flux is equal to the turns ratio of the transformer. If 5M is much bigger than the 5LP, or 5M is much bigger than the 5LS, which means the mutual flux is much bigger than the leakage flux at the secondary side, and the flux leakage, the mutual flux is much bigger than the 5LS, this one. So we can put this equation. So next slide will show you how. Just now we talked about this one, right? How we get EPT divided by ES equals to NP divided by NS, which is equal to the turn ratio. And now, if my mutual flux is much bigger than the flux leakage primary, so this can be omitted, can be deleted. This one also can be deleted. If let's say this is much bigger than this one, this is very big, this is very small. For example, this here may be 1000, this is 0.001. This may be 1000, this is 0.001. So this can be omitted. Then I can put as a VP equals to EP, VS equals to ES. Then I use this equation. I can have VP divided by VS equals to NP divided by NS, which is equals to A. Okay. So next we talk about the magnetizing current in a real transformer. Same, we open on the secondary side. We inject the current, AC current, in the primary side. When an AC power source is connected to a transformer, a current flows in each primary wide circuit, even when the secondary circuit is open circuited. The current will flow inside in the primary winding, although this is a open circuit, no load. The current is the current. This current is the current required to produce the flux in a real ferromagnetic core that consists of two components. One is a magnetizing current, IM, current required to produce a flux in the core, and also the core loss current, IH and IE. which is current required to make up for hysteresis and aiding current loss in the core. As overall, total no-load current or excitation current IEX equals to IM plus IH plus IE.